Hi guys, I'm Kaur. Welcome to my channel. Today's focus is going to be titrations, a topic that's high yield on the MCAT and a topic many students seem to be struggling with. So I'm going to break it down into two videos. Today's video is going to be focusing on the fundamentals, understanding titrations, and learning how to use the related equations to solve for certain variables. The second video is going to focus more on buffer systems, how to use the Henderson Hasselbalch equation, as well as read titration curves in depth. So if you already have not, don't forget to subscribe to my channel. Without further ado, let's get started. What is titration? For me, titration is just cancellation. So you have one thing, you're trying to add the equal amount of another thing in order to cancel them out. And this is called neutralization. So let's say you began with acid, you add base in order to neutralize it, in order to cancel it out. And this point, when both are equal, both have equal number of moles canceling each other out, this is called the end point or the equivalence point. And that makes sense because the number of moles of acid is equal to the number of moles of base. Now, to go into a better understanding of how to solve for these moles or the concentration or the volume used and everything, how to solve for these variables, which equations to use, I'm going to focus on three different questions. Let's begin with the first one. 1 molar ammonia is titrated by 10 mL of 0.1 molar HCl. How many molecules of NH3 are present in the solution titrated by 10 mL of 0.1 molar HCl? So here I've taken out key pieces of information from the question. So let's just go over it again. We're trying to titrate a 1 molar solution of ammonia with HCl, and we're told that 10 mL of the 0.1 molar HCl was able to completely titrate the 1 molar ammonia solution. Now, the question is asking us for us to solve for molecules of ammonia. Before we go on, I want to make a list of things that you should have known in order to be able to solve this question. So, first thing is the molarity equation. So, concentration is equal to the number of moles divided by liters. Now, it's very important to remember units in this case. As you can see, our question gave us the volume in mLs. So remember that at some point you will be converting from ml to liters. Now, the second equation that you need to be familiar with is M1V1 equals M2 times V2. So we'll have three of the variables and we'll be solving for the fourth one. Now, the third thing is key in order to be able to solve for the molecules of ammonia. And for that, you need Avogadro's constant. And that is 6.02 times 10 to the 23rd. So you have to be able to convert from moles to molecules. So let's get started. We have M1V1 equals M2V2. Now the M1V1 refers to our HCl, the M2V2 refers to our ammonia solution. So we know our concentration, it's 0.1 molar HCl times the volume. So now remember that this has to be in liters, or if you are to keep it in milliliters, that the volume that you get for V2 will also be in milliliters. So just keep track of your units. For now, I'm just going to leave it in milliliters. So we use 10 milliliters of HCl, which is 0.1 molar solution, in order to titrate a 1 molar solution of ammonia, and we're solving for the volume of the ammonia solution that we were titrating. If you do the math, you can see that V2 equals 1. Looking at the units, we know that the volume is still in milliliters, so we get 1 milliliters. And if I was to convert this to liters, I'll just show the dimensional analysis here. 1 liter has 1,000 milliliters. That would give you 0.001. The units cancel, we're left with 0.001 liters. So our concentration here is 1 molar, and we know that we have 0.001 liters of it. Now, we're not done here. So far we've only figured out, we knew the concentration of ammonia, now we know the volume of ammonia. From this, we can figure out moles. And the way we do that is through the molarity equation that I showed before. So 1 molar equals how many moles if we have 0.001 liters. If you solve it out, you get 0.001 moles. Now, the next step is to convert from moles to molecules. And that requires the use of the Avogadro's constant. So we're going to take our moles, multiply it by the constant in order to get our number of molecules. Now, this is something that trips up a lot of people, so be careful when you're doing this math. Now, this is a simple number. It's just 1 times the 6.02. What matters is the exponents. So 0.001 is 10 to the negative 3 moles. So that's another way to write it. Now, when you're multiplying exponents, you add them. So this would give you 6.02 times 10. So 23 plus negative 3 is 20. So that tells us that our answer is B. Now, I want you to pay attention. You could have gone through everything and messed it up at this last calculation. So it's very important, and I'm going to emphasize this, to know your exponent rules. When you multiply exponents, you add them. When you divide exponents, you subtract them. The second part of the question asks, at the equivalence point, what is the pH of the solution? A, is it equal to 7? B, is it greater than 7? C, is it less than 7? Or D, it can't be determined. The second question is a conceptual question. It does not require any sort of calculation. It just requires an understanding of acids and bases. So for this question, you need to know what kind of base and what kind of acid you're working for. It could be a strong base, strong acid, weak base, weak acid. So we know that HCl is a strong acid. Ammonia is a weak base. If you're wondering how to determine whether it's weak or strong, you have to memorize all of the strong acids and all of strong bases. So there's 7 strong acids and 8 strong bases. Whatever is not strong is weak. So pretty much you only have to memorize these 15 acids and bases, and anything else is weak. Now, this being said, let's go over how to determine pH. So we know that pH is negative log of the concentration of H plus ions. So in order to know what the pH is, we need to understand what's happening in the solution. So we have NH3 plus HCl. When that reacts and neutralizes, we get Cl minus ions plus NH4 plus ions. Now, when these two react, we have 0 concentration of NH3 left and 0 concentration of HCl left. That's what neutralization is. And that leaves us with NH4 plus in our solution, which is a acid. Even though it's a weak acid, it is an acid. And that's why after neutralization, the solution's pH leans more towards the acidic conditions because we have this weak acid in our solution after it's been titrated. Now, something you should know for all cases, I'm just going to go over all of the possible scenarios. So, scenario 1, if you have strong acid, I'm just going to shorten it, plus strong base. These two, when combined and neutralized, we get 7, exactly 7 as our pH. When we combine a strong acid with a weak base, we get pH less than 7. Why? Because the conditions are more acidic. We form a conjugated acid from our weak base. So we have our weak base in the solution. When reacting with a strong acid, it produces a weak acid. Therefore, our pH is less than 7. It's a little more acidic. In the third condition, when we combine a weak acid with a strong base, the opposite happens. We have a pH greater than 7 because when a strong base reacts with a weak acid, a conjugated base forms in the solution, therefore making our pH greater than 7. Knowing all of this, now we know that our answer is C. Our pH is less than 7 because we have a conjugated weak acid in our solution after titration. The third part of the question asks, in this case, which pH indicator would have been the most useful for titration? A. Thymol blue, B. Litmus, C. Methyl orange, or D. From Crescel green? The third question is very similar to the second question in the sense that they want us to figure out the pH indicator range that could have been used in this situation. So in the last question, we determined that the pH of the neutralized solution is less than 7. So when the endpoint is reached and enough HCl was added to the ammonia solution at the endpoint, that's what it's called, the pH was less than 7 because we form NH4, NH4 plus, which is a weak acid. Now, when determining range for your pH indicator, there are two things that you need to keep in mind. One, the range has to be as narrow as possible. And the second, your pH, when the solution is neutralized, has to fall within that range. So let's take a look at our answer choices. First, let's eliminate the extreme situations. We know that our pH has to be something less than 7. Therefore, A gets eliminated right away. C, methyl orange, with a range of 3 to 4, is too low in pH to be able to detect the pH change when neutralization happens. So, this can't be the answer either. Now, we're left with choice B and D. Technically, both can be utilized in order to detect the neutralization. However, if you were to pick the best range, remember the two things we said. Our pH has to fall within the range, and the range has to be as narrow as possible. So keeping that in mind, the correct answer would be D, because it has a smaller range compared to litmus. Well, that's it for the first part of the titration video. The second part will cover the buffer system, the Henderson Hasselbalch equation, pKa, Ka, as well as the titration curve. So stay tuned, check out my other YouTube videos, like, comment, let me know any feedback, criticism, any topics you want to see in the future. But most importantly, do not forget to subscribe to my channel.